All right, so this one's going to be about enzymes. So first, enzymes as biological catalysts, their properties are that they lower activation energy. That's normal with any catalyst. That's how they're able to like speed up reactions. So it increases the reaction rate. But just remember that doesn't alter your equilibrium constant. So your KEQ will be the same regardless of if you have a catalyst or not, because the catalyst basically is going to speed up the reaction in both directions, so the equilibrium will stay the same. Enzymes are not changed or consumed in the reaction, and they're specific for a reaction or class of reactions because it's the way that they bond, that they're very specific. So if it's for a different substrate or something like that, it won't connect properly, so it won't work. It's also pH and temperature sensitive, meaning that if you have a pH that's too high or too low, temperature that's too high or too low, it also would affect the catalyst working, the enzyme working and attaching properly because of the substrate. Also, they do not alter overall delta H or delta G. Just a reminder, delta H is enthalpy, the change in heat content. Delta G is the change in free energy. So just think of Gibbs free energy. G, Gibbs, you know. Yeah, so those are the properties of an enzyme. Classification, there's a bunch of different types, and the way to really remember them is that they're going to end with ACE. So we have oxidoreductase, we have hydrogenase, reductase, oxidase, transferase, hydrolase, lyase, isomerase, ligase, and all of those, you just really have to use the prefixes, the root words, to try to figure out what they're going to be. So oxidoreductase, just think oxidation, reduction, reaction, right? And it's an enzyme to speed that up. So this catalyzes redox reactions. So just to remember the oxidation, reduction, like which one is which, think of oil rig. So oil is loss of electrons, reduction is gain of electrons, right? And the reducing agent will be oxidized, and the oxidizing agent is going to be reduced in the final product. So the reductant is another term to know for the MCAT. Reductant is the electron donor, and it's the reducing agent. So reducing agent and reductant mean the same thing, and if you just remember, the one that is doing the reducing will be oxidized because it has to be the opposite. So since it's oxidized, it's losing electrons, meaning it's donating electrons. So just putting all those pieces together. Oxidation is loss of electrons. Oil. Oxidation is loss of electrons, meaning it's donating them. So it's an electron donor, and that's also the reductant and reducing agent. Oxidant is the electron acceptor, and just remember the oxidant is the same as an oxidizing agent, meaning it's reduced. And reduce, if you think of the oil rig, reduction is gain of electrons. So it's accepting the electrons from the reducing agent. So yeah, those are oxidoreductases are going to be enzymes that catalyze redox reactions. And hydrogenase or dehydrogenase, just think it's catalyzing dehydrogenation. Dehydrogenation reactions. Reductases and oxidases are in specific oxidation reactions, specific reduction reactions. It'll be catalyzing those. Transferases, there's a few different kinds of transferases, but of course you can figure out by the name, it's for transfer, for moving things, right? It can catalyze group transfer. Think of it like a truck. moving a bunch of things over like a cellular membrane or something like that. A kinase, which we're going to see a lot in like glycogenesis and glyconeogenesis and all those that I'll get to later. Those all have kinases in them. So kinase catalyzes phosphate transfer. There's different kinds. Like an example would be enterokinase. Entero means intestine. That's how you think of it. And that activates pancreatic enzymes. So the kinases are just to transfer phosphate. Okay, hydrolase is another category, and it catalyzes hydrolysis reactions. And if you think of like a hydrolysis, you break those words down. Hydro means water, lysis is breaking down. So you're breaking something up with water in a hydrolysis reaction. And hydrolase, which sounds similar, is going to be that enzyme that catalyzes that. So phosphatases are examples of this, and they cleave a phosphate group from a molecule to aid in breaking it apart, and that's how it lowers activation energy. A lyase is another category. In the same way that we looked at lysis, it's going to be the ly group means breaking apart. So lyases are breaking, but not with water, because that would be a hydrolase, right? So lyase is breaking apart without water and without moving electrons. So it catalyzes the cleavage of one molecule into two without requiring water or without acting as an oxidoreductase, meaning it's not moving electrons around. It also catalyzes synthesis reactions, so it can be called synthase as well. Isomerases catalyze bond rearranges. It can be between stereoisomers or structural constitutional isomers. So yeah, it's changing the bond arrangement, the bond orientation. That's what an isomerase is. So you just think of an isomer, so you have stereoisomers, structural or constitutional isomers, and that's what the isomerase is going to be used for. It'll catalyze the bond rearrangement. Many are also classified as oxidoreductases because they're moving electrons around, or as a transferase, or as a lyase because it's breaking things up, it's moving things. So I guess this would be like another more specific term just to know, but isomerase, just think of isomers. Okay. Ligase is different from lyase because lyases they're these, everyone thinks they're really important, but lyases only catalyze small reactions, even though it's a big fish molecule. So it's lying lyase by making it seem super important when it's really just working with super small reactions. Ligase, on the other hand, think of the G in ligase. It'll have giant molecules. That's what it's catalyzing large reactions or addition or synthesis reactions between large molecules. That's what ligase is used for. And it often requires ATP. It's often encountered in nucleic acid synthesis and repair. Those are DNA ligases, so those are important to keep in mind. Those will probably come up when we're talking about the cycles later. Activation energy. That's what's lowered when we're talking about catalysts. They lower activation energy so that the transition state is lower and it's easier to complete a reaction. It's faster. So endothermic reactions, this is just a review, endothermic reactions require energy and it'll absorb heat. That's what you usually think about. So it's usually the surroundings are introducing heat into the system. Endothermic, it's going into whatever you're dealing with, into the reaction. And delta H is going to be greater than 0. Remember, that's enthalpy. Delta H is enthalpy, and it's going to be greater than 0 because heat is going in, right? Exothermic reactions, energy is released into the surroundings. And so delta H is going to be less than 0 because you're going to have a negative delta H since heat is going to be leaving the system. Endergonic reactions. So when we're talking about endergonic, that's that G in there is going to remind you that we're talking about delta G. And that just means that there's more free energy in the system. So delta G is going to be greater than 0 in an endergonic reaction. Exergonic is where delta G is going to be less than 0. And that'll be a spontaneous reaction because delta G is less than 0. Just remember that. Exergonic is spontaneous. And the G in there also, just remember, that's talking about delta G, Gibbs free energy. So first, enzyme substrate binding. So obviously, the enzyme has to bind to a substrate for it to work in a reaction. And it's very specific usually. So enzyme specificity is super important. Substrate specificity varies, but most enzymes are very specific. So it's because there's an intimate interaction. It's based on structural complementarity and mutual recognition. There's linkage specificity also with enzymes. So this is specific to a type of bond present in the molecule. That means that certain enzymes require a specific bond. For example, alpha amylase cleaves at alpha 1,4 glycosidic linkages. So it needs a certain type of bond to be able to connect properly. Then there's group specificity. It's specific to a type of bond and the surrounding structure. So an example is hexokinase phosphorylates any 6C sugar. So anything that looks like that, with even if it's different surrounding structures maybe, or different types of molecules bonded to it, the basic structure is 6 carbons in a sugar, and that'll be able to bond with the hexokinase regardless because it's the group specificity. Also, chymotrypsin cleaves at the carbonyl end of amino acids with aromatic R groups. So again, that's not as specific as needing a specific molecule bonded on there, but it needs the general group to be similar so that it can match up. Absolute specificity is kind of what I mentioned before about the shape, and that's specific to a single substrate. So renin hydrolyzes angiotensinogen to angiotensin 1. That's the only thing that it will work with. So it's just a single type of substrate that it'll connect with. That's absolute specificity, which is clear by the name. There's also stereochemical specificity, meaning it's specific to a particular stereoisomer. So that means even if you have a slightly different arrangement of the bonds, even if it's the same structure, the same general molecular formula, the stereochemistry will affect the bonding as well. And an example of that would be L-aminopropanol dehydrogenase oxidizes L1-aminopropa-2-ol to aminoacetone. So it's like it will only do the L version of it, not the D version, because those stereoisomers are going to have different shapes and not be able to connect properly. The reaction catalyzed is usually very specific. The side where the S binds, the substrate binds, is called the active site. And so in a lot of the diagrams that you're going to see, they'll say A site or active site on them. There's no wasteful byproducts. Every product that you have is going to be useful, and the products that you make along the way are just going to be intermediates or transition states, and those are usually going to be transformed or conformed into something else. So one thing that was mentioned in the videos that was said you had to understand but not necessarily do a bunch of calculations for was the Michaelis-Menten equation, which is V equals V max of substrate concentration times substrate concentration over Km plus substrate concentration. So V max is the max velocity, max reaction velocity at saturation. And that shows in a diagram that they'll probably show you, which is a hyperbolic curve. And on the y-axis, you have the reaction velocity, V. On the x-axis, you have substrate concentration, S in little brackets. And the line is going to be hyperbolic and end at Vmax, which is at saturation. And that's actually one thing that I saw in the practice test was that you can't go past Vmax because you're already saturated. So the reaction velocity won't be going anymore. It'll stay exactly where it's at because you can't go any faster or further. At 1/2 Vmax, that is where you're half saturated. So I think when you, that's what Km is. Km is the substrate concentration at 1/2 Vmax. So the Michaelis constant is a measure of the enzyme's affinity for the substrate. It's inversely proportional and has intrinsic property. So the higher the Km, the lower the affinity for the substrate. That's one thing to remember. So Km is the Michaelis constant, the measure of an enzyme's affinity for a substrate. But Km is 1/2 of Vmax. Remember, Vmax is the max velocity at saturation. So Km is the substrate concentration at 1/2 Vmax. And that is inversely proportional to the enzyme's affinity for the substrate. Also, the energy is not shown on this specific graph, but it affects the rate. So V and Vmax are directly proportional to the energy in the reaction. Okay, then also, so that's the Michaelis-Menten equation. The next equation, or the view that you're supposed to understand, is the Lineweave-Burke plot, and that's the double reciprocal plot of the Michaelis-Menten equation. So this plot can be used to determine Km, remember the Michaelis constant, and Vmax, the max velocity at saturation. On the graph, it'll be going on the y-axis, it's 1/V. So instead of in the Michaelis-Menten equation, you're going to have the y-axis as the reaction velocity, just V. This one is a reciprocal, so it'll be 1/V in the form of seconds over micromole, I believe. And then on the x-axis, you will have 1/, the concentration of the substrate. So this is just literally double reciprocal. The same things that you have in the Michaelis-Menten equation, the V over concentration of substrate, it's going to be the exact reciprocal. So it'll be 1/V and 1/ the concentration of the substrate for the Lineweaver-Burke plot. And you're going to have your x-intercept will be -1/Km. Your y-intercept will be 1/Vmax. And so those are the ways that you can, if you get either the first plot of the Michaelis-Menten plot, or if you get the Lineweaver-Burke plot, with either of those, you should be able to figure out Km and Vmax. Remember, in the Michaelis-Menten equation, Km is 1/2 of Vmax, or is the substrate concentration at 1/2 Vmax. In the Lineweaver-Burke plot, the x-intercept is equal to -1/Km. And to find Vmax, on the first plot, you can find it just by literally plotting it out, right? Because you can just calculate it and see what the distance is. For the Lineweaver-Burke plot, your y-intercept is going to be 1 over Vmax. Okay. All right, cooperativity of enzymes. Multimeric enzymes are going to have multiple subunits and multiple active sites. Michaelis-Menten plots are going to be sigmoid and have nonlinear Lineweaver-Burke plots. So instead of having the hyperbolic curve in the Michaelis-Menten plot, you're going to have something that's a little bent this way and then this way. So that's going to be different. And then that's going to cause you to have a nonlinear Lineweaver-Burke plot. Because normally you have a line like this, your x-intercept is -1 over km, and your y-intercept is going to be 1 over Vmax. But in this case, your Lineweaver-Burke plot is going to be nonlinear because you have this sigmoid curve, and then you're going to have the double reciprocal of that. This is the characteristic of regulatory enzymes. An important thing to remember is the difference between T state and R state. So T state, taut. Think T, taut. So super tight, and it has a low affinity because it's so close together, so scrunched. Just think of someone at a party who literally is just so like in their own bubble, and there's a low affinity to hang out with them. You know, it's hard to interact with them. They don't have a lot of people around them because you don't really want to interact with them because they're just so tight and like stuck up. I don't know. So T state, taut. R state is relaxed, it's super chill. Think of that cool person at a party or something in your class, and they're just so easy to like go approach. And so that's a high affinity. You can easily go up and talk to them. They're always gonna have people around them because they're just so fun and cool. Yeah, that's it. That's good. So T state, taut, low affinity. R state, relaxed, high affinity. All right, homotropic and heterotropic effects. So positive homotropic effects are going to be the binding of one equivalent of S enhances binding of additional equivalents of S. With homotropic effects, the negative would be binding of S discourages binding of additional S. So it can have two different scenarios, I guess. So it can enhance binding of additional equivalents, but it discourages binding of additional S substrates. For heterotropic reactions, the positive heterotropic effect will be that effectors influence binding of another species in allosteric activators. Allosteric just means, allo means other. So allosteric activators are not the active site, it's in a different place. So effectors influence binding of another species in non-active sites. That also means that there's allosteric inhibitors, so this can be inhibited in the allosteric sites. Okay, we're going to talk about the basics of enzyme activity. The reason we use enzyme activity to measure the amount of an enzyme in a specific reaction is because the precise concentration of enzymes is pretty hard to determine. That's the E with the little brackets around it. That means the concentration of catalytic centers, but it can also mean enzyme concentration if you have one enzyme per substrate. Also, for the MCAT, enzyme activity, enzyme velocity, and enzyme rate are all used synonymously, so keep that in mind. So the amount of an enzyme is instead described by activity. The enzyme unit is in micromoles over minute, or Katal, which the symbol would be KAT, and it's equal to moles over seconds. Specific activity is enzyme units per milligrams of protein. So it would be that symbol U for enzyme unit over mg. And it's a measure of Measure of enzyme purity is a measurement used during enzyme purification. Those are important terms to remember. So the effects of local conditions on enzyme activity, it can be affected by temperature, pH, salinity. Those are all the common ones that can affect proteins and denature enzymes. So for temperature, every 10 degrees Celsius increase doubles the velocity until the optimum temperature is reached. So as it gets warmer, up until that optimal temperature, the reaction rate will increase, so the velocity will increase. But the optimal temperature for the human body is around 37 degrees Celsius, which is 98.6 degrees Fahrenheit or 310 Kelvin. T temperature is proportional to kinetic energy in this case. But once you reach that optimal temperature, the reaction rate, the velocity, will decrease dramatically. So usually the graph for this will be rate of enzyme action on the y-axis, temperature on the x-axis. It'll be slowly increasing as you increase temperature. Once you reach that optimum temperature, the line just drops all the way to the bottom because it becomes denatured, they stop really working. One of the questions that was given for the prep was, what accounts for the steep decline on the right side of the plot? And the answer to that was that the enzyme denatures as temperature continues to increase past optimal temperature. For pH, most enzymes are only active over a very limited range, and most of them have an optimal pH. For enzymes in the blood, that pH is 7.4. For the gastric enzymes, it's around 2. Pancreatic enzymes, it's around 8.5. When you're thinking about neutral, people will say that our blood is neutral, even though it's 7.4. That's because the chemical neutral is a pH of 7, but the physiological neutral will be 7.4. So if you're talking about like the human biological system, and if it says neutral, they're saying 7.4 pH. For salinity, it's not usually of physiological significance, but in vitro, a high salinity can lead to denaturization. So for regulation of enzyme activity, there's different types of regulation that you can have: feed-forward and feedback regulation. Feed-forward regulation is very rare. That's when you have something early in a reaction sending messages to something later in the reaction, telling it to stop, saying like, we have enough, so you don't need to do that. But that's not the common one. That one's pretty rare. Feedback regulation is the more common one. That can be feedback activation or feedback inhibition, which is obviously negative feedback. So that would be when you're later in a reaction and you realize, oh, I have a lot of this, then you would send a feedback inhibitor, and that would tell earlier processes to stop for a moment because they already have enough of whatever they're producing. The positive feedback, which is feedback activation, would be, oh, I really need more of this. Then they send a message back to one of the earlier processes telling them to start that back up again. The equation for the enzyme substrate complex is E plus S, enzyme plus substrate, is equal to ES, because they have bonded together, and then after the reaction occurs, that it's enzyme plus product. The enzyme is not created, not destroyed, and it's going to stay the same throughout the entire process because it's not really used up or changed in any way. It just bonds to help the reaction go faster, and then it becomes separate when the product is produced. The two theories are the lock and key theory and the induced fit theory. So for the lock and key theory, you just think of a normal lock and key. The key is always going to look the same, the lock is always going to look the same, and they fit perfectly within each other. So the enzyme is always in the same conformation, and so is substrate. The induced fit theory is that the enzyme has a particular shape that it has when it's relaxed, but it'll change and conform to fit different substrates, which makes more sense if you for an enzyme to be more versatile and attached to different things with similar functions, but with different structures and conformations. So about cofactors. Cofactors are generally required by many reactions. More than one are required by many reactions. They provide chemical functions that are not found in side chains. They're usually small and in low concentrations. Most coenzymes are vitamins or their derivatives. And the difference between a cofactor and a coenzyme is that a cofactor is inorganic and a coenzyme is organic. These have looser interactions, so they're more likely to react. Versus a prosthetic group, which is tightly bound and it doesn't really attach to things or react with things very well. Two terms to keep in mind are apoenzymes and holoenzymes. So an apoenzyme is all alone, it's unattached, and so a good way to remember that would be like, poenzyme, apoenzyme, because it's all alone, nothing's attached to it. Holoenzyme is attached, it has friends, so you can think like holla at me, homie, or something. Holoenzyme is attached to things.